Hello, in this video we are continuing our discussion of section 8.1 on sequences. In example 5 here we have been asked to evaluate or find what values of r the geometric sequence, which is r to the n, is convergent. So here, a geometric sequence, this is a type of sequence that is common enough that it gets a specific name, and you'll see a little bit more about why it's called geometric when we start talking about geometric series in the next section. Geometric sequences and geometric series are related, which is one of the reasons why we are looking at where this geometric sequence converges. Another reason is that in the future, you can use the result from this video or from this example to quickly determine when or if a specific geometric sequence converges. So for example, if you're talking about, say, 1/2 to the n, here r is equal to 1/2, and in the future you can make a conclusion about whether this converges or not based solely on the r value. So that's what we're going to figure out in this example. For what values of r is the geometric sequence r to the n convergent? So we are going to figure this out by splitting up all of the possible r values. So this would be r is any real number, any constant value. So I'm going to split it up between positive and negative r values. And also we need to consider r equaling 0. So with positive r values, we will also probably want to consider r equaling 1 separately. So then we'll have the interval from 0 to 1, and we'll also have the interval from 1 to infinity. And we're going to have similar categories for the negative cases. So this would be r equaling -1 between -1 and 0, and then between -infinity and -1. So we're going to have 7 different cases here, including r equaling 0 separately. So let's start with r equaling 0, because that's a very easy case. We'll do that one first. Then we'll do our positive values, let's say 2nd, 3rd, 4th, and then we'll do our negative values 5th, 6th, and 7th. So that's going to be the order that we're going to go in here. So first case, r equals 0. Well, 0 raised to any number is just 0. So the limit as n goes to infinity of 0 of any constant is very clearly 0, which means that it converges when r equals 0. That was easy enough. Second case, r equals 1. Well, 1 raised to any number is just 1. So the limit as n goes to infinity of 1 is just 1 since it's a constant, which means this converges when r equals 1. Third case, we have r between 0 and 1. So we're going to have to just consider a general r to the n here. But if we talk about the limit as n goes to infinity of r to the n for an r value that's less than 1, for example, consider r equaling 1/2, like I wrote up here. If you take 1/2 and you raise it to a power, and then you raise it to a larger power, and a larger power, and a larger power, you're going to have, say, 1/2, and then 1/4, and then 1/8, and 1/16, and so on and so forth. The numerator stays the same, the denominator is getting bigger, so the sequence as a whole goes to 0. which means that the sequence converges when r is between 0 and 1. Next, we have our fourth case, which is r being between 1 and infinity. Again, we're just going to have to consider the general r to the n. So the limit as n goes to infinity of r to the n. For example, here let's consider r being 2. Now you're taking 2 and raising it to larger and larger powers. Because the magnitude of this is larger than 1, when you raise it to bigger and bigger powers, it's going to get bigger. So this goes to infinity, which means that it diverges here. Okay, so now we need to consider our negative values. Our fifth case is going to be when r is -1. So we have -1 to the n. If we wrote out some of our values here, if we started at n being 0, then that would give us a +1. But n being 1, we would have a -1, and then a +1, and a -1, and so on and so forth. We already saw a sequence like this in the previous lecture for this section, although it was written a little bit differently, but we ended up writing it out to 1, -1, 1, -1, so on and so forth. And we figured out that that diverged because if we have an alternating sequence, like what we have here with the signs changing, the magnitude of the terms has to go to 0 in order for it to converge. Or you can just think about the fact that this is continually alternating between 1 and -1. It's never going to approach a unique number. So this case will diverge. The next case that we have written is for r values between -1 and 0. So we're going to have to consider a general r to the n, but for example, we can think about r being -1/2. So r to the n would be -1/2 to the n. So then the limit as n goes to infinity of r to the n, this is going to be similar to the case when r being 1/2, except now the signs of our terms are going to change. But since our numerator is smaller than our denominator, then when we raise it to larger and larger powers, the fraction is going to get smaller and smaller. So even in this case, the limit is equal to 0, which means that it converges when r is between, -1 and 0. Okay, so our last case is for r values between -infinity and -1. In this case, the limit as n goes to infinity of the absolute value of n, because we're going to have an alternating sequence, this is going to end up being infinity. If we just consider the magnitude of the terms, then we would get back to this case, which we've already considered. So those are going to blow up. This means that the limit as n goes to infinity of r to the n does not exist. If you recall, we had a theorem helping us out there, which means that the sequence diverges in this case. So, in summary, this is the result that you want to remember from this example. The geometric sequence r to the n converges for, let's see if we can put everything together. We have, it converges when r is 0, when r is 1, when r is between 0 and 1. It also converges when r is between -1 and 0, but it diverges everywhere else. So we get -1 is less than r, less than or equal to 1. And it diverges for r being bigger than or equal to, less than or equal to -1, and r strictly bigger than 1. So this is the result that you can remember. So when you're applying this, if you are considering the sequence. 1/2 to the n, you could say r equals 1/2, which is less than 1, or less than or equal to 1, and bigger than -1, which means that it converges. If you have -3/2 to the n, then r is equal to -3/2, which is less than -1, which means it diverges. And it's as simple as that. When it gets a little complicated is when things are written separately. So let's say you have r to the -1 times 1/2 to the n. Well, notice you can write this as -1 to the n over 2 to the n, which can be written as -1/2 to the n. So now you're back to being -1/2, which converges. Okay, so you can use the result in this example to help whenever you are evaluating limits with geometric sequences. Also, we will revisit this when we talk about geometric series in the next section.